Today we're going to be learning Quicksort. So what is Quicksort? So in Quicksort, we're going to take the entire array, break it up into smaller and smaller pieces, sorting these smaller pieces, which ends up sorting the entire array. This idea of breaking things down into smaller and smaller pieces, solving the smaller pieces, is called divide and conquer. So here, we're going to start with our whole array. So we're going to take the left and right bounds, and we're going to find a centerpiece. So let's look at our index. So we have 0 plus 4 divided by 2, which is going to be equal to 2. So our pivot, which is what we're going to call our center, is going to be 5. So why do we pick the center? In randomly distributed data, it turns out that statistically, there is an even distribution. So there's not a bias on the left or the right of the pivot. It's sort of evenly distributed. So that's why we pick the center. If we know more about how our data is going to be distributed, we can choose smarter pivots. But here, we're just going to be choosing the center. And we're going to use this 5, this pivot, to sort our array. So there's going to be a fundamental question we're going to be asking. Is there anything on the left side of the pivot that should be on the right side? And is there anything that is on the right side of the pivot that should be on the left? Assuming that we're sorting in ascending order, we want big items to be on the right, and we want small items to be on the left. So to do this, we can illustrate this by having an I. We're going to have an I here. And then we're going to have a j here. And we're going to ask I this fundamental question. Are you greater than or equal to the pivot? Greater than or equal to the pivot. So this is to ask, is there anything on the left where I is that should be on the right? And then we're going to ask j, are you less than or equal to the pivot? So should you be on the left? And once both of these questions are satisfied, so we're going to keep asking I this question, moving it forward and forward, and it's going to pause once it's satisfied. We're going to ask j this question, it's going to move forward and forward until it's satisfied. Once they're both satisfied, they are going to swap with each other, unless they meet at the center, for which we will return and create our new partition. So let's go ahead and ask I this question. Is 1 greater than or equal to 5? No. So we're going to move forward. Is 0 greater than or equal to 5? No. We're going to move forward. Is 5 greater than or equal to 5? Yes. So we're going to stay there. We're going to go to I, and we're going to ask, is 3 less than or equal to 5? Yes. So we're going to pause there. Once we're both paused, we're going to take I and j and swap them. So 5 and 3 are going to swap. And then j can continue. Is j is going to move forward. Is j, or 7, less than or equal to 3? No. We're going to move forward. And I and j are on top of each other, so we're done with that partition. So to find a new partition, we're going to take our last pivot and use that as our next right bound. So the last partition was here, so we're going to use that as our next right bound. So let's go ahead and do that. So we're going to have 1 and 3. Remember, we're not splitting up the array to make a new array. We're just looking at different partitions or subsections of our array. So we're going to get this nice 103 here, which is going to naturally split up the next part of the array, which is 7 and 5. We're going to first evaluate all the way down to the left side, then pop back up to the right side once we're done. So let's go ahead and do this again. We're going to have I, so I here, and then we're going to have j here. Now we're going to have to find our pivot again, so we're going to have to look at our indexes. That's going to be 0 plus 2 divided by 2 floored. That's just going to be equal to 1. So 1 here, so this 0 is going to be our pivot, and now we're going to ask the same questions again. Is 1 greater than or equal to the pivot, which is 0? Yes. So I is going to pause there. And then j is going to ask, is 3 less than or equal to the pivot? No. Now, is 0 less than or equal to the pivot? Yes. So we're going to pause there. Now, we're going to perform the swap. So let's perform the swap up here. We're going to take 1, we're going to take 0, and we're going to swap them. Now I is going to continue. It's going to move forward, And now we're going to see that I and j are on top of each other, so we are going to return. Now the next partition, since our pivot was last 0, which was at the 1 index, we're going to have a new partition over here, have 0 and 1. And then again, we're going to ask the same question over and over again. So I is here, and then j is here. And then we're going to find our pivot. So 0 plus 1 is 0 plus 1 divided by 2. That is going to be equal to 0.5, but since we're flooring it, that is just 0. So our pivot here is 0, and that means I can't move anywhere. So it's going to stay where it is, paused. And then j is going to ask that question. Well, 1 is not less than or equal to 0, so we're going to move forward, and we're on top of each other. So we're going to return. And then we see here that we're going to get this 0 and 1, which is going to be our base case because I and j would just be on top of each other. So this part is solved. We're going to go back up and find this partition. 3 is by itself, so we can't do anything. And we pop back up and we see that we have solved this entire left portion. So we're going to go to the right and continue asking these questions on the right. We're going to have our I here, and then we're going to have our j here. Ask the same questions. Let's find our pivot. We're going to do 3 plus 4 divided by 2 floored. That's just going to be 3.5 floored, so that's just going to be 3. So our pivot here is on I, so I can't move anywhere. And then j is going to ask, is 5 less than or equal to 7? That is correct. Now we are going to swap I and j, so I and j swap. Now j can move forward, I is going to stay still because it's stuck on that pivot, and j moves forward, and we see that I and j are on top of each other, so we're going to return. Now this is going to create the natural partition of 5, and then we're going to get 7. So now we're all on the base cases, so that means our entire array is sorted. This is Quicksort. Quicksort has 3 parts. It has sort of a setup, so a driver, so it has some sort of driver function. This sort of just sets up how we're going to use Quicksort, and then we're going to have a splitter function, so how we're partitioning sort of these pivots. Then finally, we're going to have the sorting function where we're sorting back and forth with our pivot that we have just chosen. So this is going to split into subarrays, split into subarrays. And this is going to sort along the pivot. Sort along the pivot. Now let's jump into these. Let's define the driver. Our driver, so what we give to Quicksort is some array. And what Quicksort needs to do is convert this into something it can start running the algorithm on. So the first statement that we're going to see is that we're going to call the split function. The first split function call is going to be the array itself. We're going to pass the array. It's going to be our left boundary. So the left boundary starts all the way at index 0. And then we're going to give it the right barrier. So that's going to be the length of the array minus 1. So that's the driver. That's the first bit. This next bit is going to be our splitter. So the splitter here is going to actually create the subdivisions that we're going to be working on. So we're going to take that array that we just passed. We're going to take that array, and then we're going to take the left barrier and the right barrier. The driver just gave us this. So now we're going to say, if this is going to be our base case, we're going to stop running this splitter. We're going to stop splitting if the left, so this condition must be true to keep going. So if the left is less than the right, as we saw with the array before, we had I and j right on top of each other on the same index. So no longer is left less than the right. So there's no way we can split this anymore. So this is going to be our base case. And now what we're going to do first is we're going to run our sorting algorithm. So we're going to run our sorts. We're going to run our sorts on the array with the left, and the right, And we remember every time we sorted, we returned j. So j became the new sort of right barrier, the new right barrier. So we're going to take that, and that's going to be equal to the new barrier. So let's call it the new midpoint. It's the new midpoint. And then after we take that, we're going to run splitter again. So we're going to do recursive calls. So we're going to run splitter, and it's going to look similar to before. We're going to keep passing the array. So we're going to take the array, and then we're going to give it the new left and right. So the first time we're going to keep left, and then we're going to give it the new midpoint. We're going to give it the new midpoints. Then we're going to call splitter again, and then we're going to first we give it the array, and then we're instead going to call it on the mid plus one to get that sort of right half subarray, And after that, we're going to give it the right barrier, And that's it. That's the splitter function. That's what's splitting and subdividing. Let's move on. Now we're going to create the sorting part of the algorithm. So we're going to do sorts, and we're going to take the array. And the left barrier and the right barrier. And as we saw before, we immediately, at the beginning of our step, create that pivot. So we're going to create that pivot, and we calculated the pivot by saying left plus right divided by 2, and then we're going to floor this. Now, the way I'm going to set up I and j here is going to be a little weird, so stick with me. So I'm going to say I is going to be equal to left minus 1, and I, or j, is going to be equal to the right plus 1, You'll see why in a moment. So now we're going to do this while loop here. We're going to create a while loop down here, and we're going to say while, and we're just going to say true. So we're just going to say while true, we're going to do these two actions. So I'm going to move down. So we know I and j in the pivot. So while true, what actions are we going to do? Okay, now here the question begins. We're going to say while true. So remember the question we asked. While true, we're going to say I is equal to I minus 1. So initially we set I to be plus 1, or we want to do I plus 1 here. Initially we set I to be equal to the left sort of minus 1, and j to be equal to the right plus 1, and we're going to see why we did this here. So to set up this while loop, we initially set I to be plus 1, so that's the reason why we first decremented it. Now we're going to ask the question we've been asking this entire time. We're going to ask if array I is greater than or equal to the pivots, so greater than or equal to the pivots, then we're just going to break. We're going to break. Let me get something thicker there. We're going to break. So this was that question we kept asking, is I greater than or equal to the pivot? No, and we kept going forward and forward and forward, and we're going to eventually hit the pivots, and then we're going to eventually break. And we're going to ask the same question to j, but sort of in the reverse fashion. We're going to ask j. So j is going to be equal to sort of j minus 1. That's why we initially did right plus 1. That's why I initially did right plus 1. So now we're going to say if array, let's preemptively put pivot here. If j, if this at this index, if this number, the number at this index, so if j, so the index of j, if that's less than or equal to the pivot, we're going to break. Now we're going to sort of go a little bit more below here, and we're going to ask, so out of these, after we've broken out of these, so after we've broken out of these, so I'm going to try to make this more clear delineation. After we've broken out of these, we're going to ask this simple question. If I is greater than or equal to j, so if j crossed I here, I want us to just return j. And now j, after this return statement, is going to become that midpoint we saw. Now, if this is not the case, then let's perform that swap. So if we go down a little bit more, we're going to do array. We're going to say array I. This is going to be some quick notation. This notation is just going to denote that they swap array j and array I. So this was quick notation. This means that this j entry goes to here, and that this I entry goes to j. So this is just a shorthand for swapping. This is possible in Python. But you still, if you can't do this, you're going to have to sort of have a temp variable there to make the swap happen. Now, what is the running time of this? The running time of this is n log n. If you want to learn how to evaluate recursive function like this, or any recursive functions like this, we have a video on that in the description below. But how does this sort of function degrade over time? What is a way we can choose the pivot such that this algorithm doesn't run in O of n log n, it runs in O of n squared, So how can this algorithm degrade over time? Say we have an already descending piece of data and we wish to sort it in ascending order. If we choose the pivot to always be the last element in this, the pivot to be the last element, I here is going to have to make the journey all the way over to the right, swapping elements, but it's only going to be swapping with this pivot. J here can't really do anything. J here is just going to be sitting here, and we're going to read all n elements. So if we were to have n elements, we're going to read all n elements. And by the time, we're going to only have this last element sorted. So when we make our new partition, we're just going to make it n minus 1, excluding the previous pivot, because this portion is already sorted. So now we're going down. If we choose the pivot to be the last element again, then we're only popping off one element, so it's going to be n minus 2. So we're only decrementing one each time. Vice versa, where we chose to split in the middle, we got nice halves over and over again, so we were splitting up our solution. Here, we're only sorting one element at a time. This is going to degrade, and so if we go to n minus 2, n minus 3, and so on until we get n minus n, this is going to end up being a n squared, a big O of n squared runtime, essentially a nested for loop, because we're going to go down n times. And even though we're doing n minus 1 and n minus 2 and n minus 3, this is essentially going to collapse still to n. This is called the arithmetic series. We go over in depth in this on our big O notation video. But essentially, if you see this degrading, sort of this decreasing by 1 each time, it still ends up being n. So we're going to have n times n since we go down n times, which is going to give us this n squared. Versus if we were to split it in half, we would get that nice O of n log n. And for the vice versa scenario, if we were to have a piece of data that is already in ascending order and we wish to sort it in descending order, and we pick the pivot to be the first element every single time. J here is going to have to keep swapping and swapping and swapping only with this last element. And again, our subdivisions are just going to be 1 minus the pivot each time, which is big O of n squared. And that is the end of the video. If you enjoyed, don't forget to like and subscribe. If you are looking for more content and implementations, there's an open source textbook in the description below. Anybody is welcome to contribute or open an issue if you find any grammar mistakes or just want to help out. With that, thank you.